Hi there, this is Professor Shannon Gracey from Miracosta College. Today we'll be covering section 4.5 from the Larson and Edwards text. This is called integration by substitution. It is absolutely imperative that you understand this section and know this section not only for the rest of this course, but for the rest of your calculus life. So here we go. A lot of this section, just a word of warning, is you need to just practice, and you need to make sure that you mix up the problems. So like the problems from sections 4.1, 4.4, and 4.5, if you just like write problems down, cut them up, throw them into a hat, and then draw it out of the hat, and you can integrate them without looking, then you're going to be okay. But what happens is people, they think that they know how to do it because they're looking at their notes or their whatever. They know it says use substitution to do this, or use blah 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 to find this indefinite integral, or evaluate this definite integral. You're not going to have that on the exam. I'm just going to give you a bunch of problems, and you're going to need to know what strategy to use. All right, so with that said, why don't you guys go ahead and warm up, either find the indefinite integral or evaluate the definite integral of these problems below. On your mark, get set, go! You can do it! Okay, let's see how you did. So this first guy, what do we have? Secant at x times tangent at x is the derivative of, beautiful, secant at x with respect to x. So our result is secant at x. Am I done? No, good. We have to add our constant of integration. With indefinite integrals, you're going to have a constant of integration added at the end. With definite integrals, there will be no constant of integration added. All right? Okay, so what about this guy? What do you think? Now be careful. Do we have a formula? I know we could separate we can separate the integrand and make it two integrals, but do we have a formula for sine squared at x or cosine squared at x? No, we don't. We have a formula for sine at x, that just to the first power, or cosine at x, that quantity to the first power, but we don't have one for the square. So what does that mean? You got it, trig identity. So we are going to work on simplifying the integral. Sine squared at x plus cosine squared at x is just 1. So now we're going to be integrating 1 with respect to x. So just so you can match it up, this quantity here using the Pythagorean identity is 1. And completing the integral, you'll get x, am I done? No, plus c. Beautiful. How many of you guys got it right? Awesome. How many of you guys made up your own power rule for that? Well, at least you knew the power rule, right? So now you just got to get everything down and make sure, you have that list of integrals next to you while you're learning, and make sure you're following existing, vetted rules instead of making up your own math. All right. What about this guy? Can I just do the integral of, integrate the numerator and then divide by the integral of the denominator? Hell no, right? That's a big hell no. You don't do that. What you have to do at this point in time, you look at this, and what was that A word? Not a bad word, starts with an A. Algebra. Right? Algebra. So you either think, okay, does this factor, or hey, what about long division? Long division works. 5x squared minus 7x's minus 6. We're dividing that by the quantity x minus 2. So we'll get 5x for our first term. I should probably write it further over. 5x's for our first term. When I multiply through, I will get 5x squared, remember that's what you want to match is that first term, minus 10x's. But remember, you're subtracting the whole thing, so don't forget to either flip your signs or recognize that that 10x is going to go positive, and then you'll have this this new quantity that you're dividing. So we'll end up with positive 3x's, and then we're going to bring down the minus 6. So we come over here, we're going to get, awesome, plus 3. And then multiplying through that binomial, we'll have 3x's minus 6. When we subtract that, we get a remainder of 0. So what the heck does that mean? That means that this is equivalent to the integral from 3 to 4 of, great, that quotient you got, which was 5x plus 3 with respect to x. So this is all our side work over here. And now we will get, using our power rule, remember we'll get 5x squared over 2, right? And then plus 3x. And then, do we need the plus c? No, because we are integrating a definite integral. So we're going to go from 3 to 4. So now, evaluating at our upper limit of integration, we will have 5 times 4 squared, that's actually 5 halves, times 4 squared plus 3 times 4 minus 5 halves times 3 squared plus 3 times 3. Continuing, we'll get 4 squared is 16, right? So we'll have 5 halves times 16 plus 12 minus 5 halves times 9 plus 9, which is going to give us, let's see, this will divide out some of the 16. So we'll get 52 in that first integral, and then over here we'll get what? Minus, so 45, so we'll have minus 45 halves, and then minus 18 halves. I rewrote that 9. So getting them all in terms of halves, so this would be what? 104 halves minus, so when I combine those, I'm going to get what? 63 halves. Okay, so far the 45 and the 18 to combine to be 63. And then finishing her off, which gives us, let's see, we'll have 1 and a 41 over 2. Here we go on our next journey here. By the way, our exam is mostly going to be on sections 4.1, 4.4, and 4.5. You will have one problem that you need to evaluate the definite integral by the limit definition. And you might have some, you usually will have something about use an area from geometry to find the definite integral. But if you're having trouble with 4.2 and 4.3, just recognize that it's good to know it, but it's not going to totally make or break you on the exam, okay? Okay, so when trying to integrate composite functions, we can use a method called or as you gain, sorry about that, more experience, we can use something called pattern recognition. to integrate the composite function without as much extra work. So just like with the chain rule and differentiation, the more you practice, the easier it is to, find the derivative without taking the time to write out all the steps, okay? Okay, so antidifferentiation of a composite function. So here is the whole plan, okay? And again, I apologize. I don't know why my boxes went away, but they did. So here's our it's a big, super important thing. So basically, the first one is when a person would use pattern recognition. The second one is change of variables. So here, change of variables is usually just called U substitution. This is our change of variables. And remember, I didn't write this on this last warm-up problem. I should have. But remember here, instead of writing just 3 to 4, I should have just said x is going from 3 to 4 right here like we did before, because what that means is that I've got it matched. You see that this here, this x, these x's match the dx, right? If I had a dt or a du, I would need to have those match. So your limits have to match your variable, your different, or sorry, it's Sunday morning. They have to match the variable you're integrating with respect to. So when you come back here and you do this change of variables where you've got this guy here, this is our change of variables, is this one here. Okay, the change of variables, you have to make sure when you do a definite integral or when you're doing an indefinite integral, there are no variables other than u in there, and you're not allowed to just pull them out of the integral. You've got to change every single x if you started out with x's in terms of u. So what I'm going to do, you've got to be able to decompose a composite function. Got to be able to decompose a composite function. So if you have, we've done a little bit of practice, right? We've done a little bit of practice, but here before, like when you're using the chain rule, right? If you have like dx of x squared plus 5 to the 10th power, right? Remember that when you first started doing the chain rule, what would you do? You'd say, 10 times x squared plus 5 to the 10 minus 1, which is 9, times the derivative of the inside, which is 2x. Hopefully, by now, you can go straight to ddx of this composite is going to be equal to 20x times x squared plus 5 to the 9th, right? So notice I didn't show as much work on that second step. So over here, when we come back to being able to do this other way, you need to recognize that you've got this composite, so you need to sort of decompose it. So if you were over here and you were taking a look at I don't know, let's say you had something like h of x is cosine squared at x, right? And h of x is this composite f composed with g at x, right? We would want you to be able to, which of course is equal to f evaluated at g at x. So you're going to need to be able to identify what's that f, what's that g. So f is that most outside thing going on. F of x is something squared, right? And g of x is good, cosine at x. So you need to be able to see that kind of stuff when you're making your substitution, All right. So here we go. Let's just, show you how to do this directly. What I'm going to do for each one, I'm going to show you using pattern recognition, okay? And then I'm going to show you using change of variables. Now, one thing to recognize is your author does it a little bit differently than I do when we're doing our change of variables. So I'll point it out later when I'm showing you some steps. So here we go. In this formula here, with the first one, which is the pattern recognition formula, what you need to do is you need to say, okay, I got to look for something that is the derivative of some inside function being raised to a power, or n as an angle for a trig function or something, right? So here you see that 2x written out, right? So we need to identify a few things, right? We need to identify what is our g of x, right? And we need to identify, okay, what is g prime of x? So in this one, what is the most complicated thing going on? Good, the quantity x squared minus 3 being raised to some power. So g of x is the inside of that. And then what you want to do, if you differentiate both sides, right, with respect to x, what's going to happen is you'll get, g of x, the derivative with respect to x of g of x, equal to the derivative with respect to x of x squared minus 3, gives us g prime at x is, good, 2 x's, right? So here, if you match up, with your formula, right, we have g prime at x is 2x. We have that. We have our inside function, g at x is equal to x squared minus 3. And so we were lucky in this problem because we had the whole g prime of x. Sometimes if we had only had an x or some other scalar or constant as a coefficient to the x and the green, then we would need to multiply by 1 and bring a constant inside and a constant outside that was equivalent to figure this out. But so far we're good to go. Now the next step is this, okay? We basically have we need to figure out what is capital F at x, right? Oh, and actually, my bad, this is bad. This should be g at x, you guys. This should be g at x. And it's probably the same all the way through. My apologies. So we need to figure out capital F at g of x. So if we look at f at x, right, is equal to, let's say f at something is equal to something squared. Do you see that? And so with this one, do you see that capital F at our something would equal to our something cubed divided by 3? Okay, so far? So what's going to happen here is we're going to go through and solve this one, all right, or find the indefinite integral. So our formula says it's going to be capital F at g of x, right? Well, capital F is our something cubed over 3. What was our something? Beautiful. Our something was x squared minus 3, right? The 2x was the price of admission, right? Do you see that in this formula here, the g prime of x goes away? The dx is an operator with this guy. So this and this combined give you an operation, so they don't remain at the end. So notice that you just get capital F at g of x plus c. So that's my capital F at g of x, and then I just needed to add my plus c. And you're done. Okay, so far? Okay. Now, doing it the other way, you literally make a u substitution. So this is what you would do. Your u is going to be that quantity that's inside the deal that's being squared. So u is x squared minus 3. Then, if you differentiate both sides with respect to x, because you've got variables in there, what's going to happen is we're going to get du dx is equal to 2x. Now, this is where I differ from your author. I isolate dx, right? So do you see that 2x dx is equal to du? That's what your author does. I isolate the dx because then you're just completely substituting in, and you can get everything in terms of u. And if the x's don't divide out, or the function of x doesn't divide out, then you know you didn't pick the right thing to do. So this here was our u, okay? And then so now let me rewrite. I didn't rewrite the integral. Sorry about that. So here we go. The integral that we're doing is this. We're doing the integral of x squared minus 3 squared times 2x with respect to x. Okay? So now we've got, this was our u, right? And what was our dx? Beautiful. Dx was this. When we isolated dx, we got that. So then what you do here is you say, okay, this is going to equal to the integral of u squared times 2x, right, times du divided by 2x. Okay, so far? So dx is this stuff, and this is our u, and the 2x is carried over from the original. But notice that these completely divide out. So when you have changed the variable, you end up with this, u squared with respect to u. But that's just a real basic antiderivative. You just get u cubed over 3 plus c, right? But what was your u? Perfect. It was x squared plus, minus 3 cubed over 3 plus c. Okay, so far? So just to let you know, most people prefer the second way I showed you, all right? I don't care which way you pick. There is one method where you do need to use substitution. So you need to know how to use the change of variables, the u substitution. But it is something that you don't have to as a rule. A lot of people like pattern recognition. Most people, when they're starting, like the u sub. All right. So here we go. Next up. So again, our basic definitions are the integral of f at g at x times g prime at x with respect to x is capital F at g at x plus c. And then the other one is the integral of f at u du is equal to capital F at u, which is the antiderivative, plus c. Okay, so first off, we'll use the pattern recognition, right? and then change of variables. Okay, so here we go. With this guy, using our pattern recognition, what's our g of x going to be? Perfect. It's going to be x cubed plus 1. And g prime of x is? Awesome. 3x squared, which do you see we have, which is really great. And f in terms of our something is what? Do you guys see that this is the integral of 3x squared times x cubed plus 1 to the 1/2 power with respect to x? So this is going to be good. We're going to get the original. So we have our something to the 1/2. So our capital F of our something, right, is going to be our something to the 3/2 divided by 3/2, which of course is 2/3 times our something to the 3/2. Okay, so now we have it set up. So here, our capital F, right, which is, because do you see that we have, let me highlight stuff. Okay, so the 3x squared is our g prime of x, right? So that's our g prime of x in our formula, right? And we're going to have our, let me make sure I use the same, the same colors. So our g of x, is this guy here. I'll do it on the rewritten one. Okay. And so now we're all good to go, right? We're going to get our capital F at our something. So the capital F ended up being 2/3 times our something to the 3/2. Our something is good, the x cubed plus 1, right? And then we're going to have a plus c. So again, you end up with your g of x inside here. Good so far? Alrighty. So now, doing the same one with change of variables, we'll have, what's our u going to be equal to? So let me rewrite the integral. And we had it as 3x squared times x cubed plus 1, that quantity to the 1/2 with respect to x. So u equals, perfect, x cubed plus 1. du dx, so I differentiate both sides with respect to x and I get, perfect, 3x squared. Now when I isolate dx, you get dx is du divided by 3x squared. So here we go. This is our dx, right? This is our u. So now the trick is, hey, we need to be able to completely divide out anything that has an x in it. So this will be equivalent to the integral of 3x squared times u to the 1/2, and then in for dx, I'm going to put du divided by 3x squared. So matching everything up, that was my dx, and my u was here. So now, using our integration formulas that we have, or no, actually, do you see that we can completely divide out the 3x squareds? And then when we rewrite this integral, it's completely in terms of u. Okay, so far? So now, using our formulas, we're going to get u to the 3/2 over 3/2 plus c. which is 2/3 u to the 3/2 plus c. And don't forget to back substitute, and you'll get 2/3 times x cubed plus 1 to the 3/2 plus c. Good so far? Awesome. Okay, so again, we need to make sure and change this guy. This should be capital F at G at X, and for the other one. Okay, now a lot of times you're going to have the essential part of G prime of X, and what that means, the essential part means, is that you have the variable portion that you need, but you're missing the scalar or the constant multiple. So what do you do when that happens, right? So here, again, doing both of them, where one, doing it both ways. What do we have? X squared times sine at. Now remember, when the power is to the right of the angle, that means the angle is being raised to that power. When it's in the middle on a trig function, it means the whole function is being raised to that power. So for these guys, okay, let's see what we got. So here, what's our g of x? Perfect. G of x is going to be x cubed. If you were doing a u substitution, you would say u equals x cubed. Make sense? Now, differentiating both sides to x, we're going to get g prime of x is 3x squared. Over here, differentiating u with respect to x, we're going to get 3x squared. But on this guy, what do we like doing? Beautiful. We isolate the dx, right, which means we'll get du over 3x squared. Coming back over here, right, our function of something, right, is sine at something. Good so far? And capital F at our something is going to be perfect, negative cosine at our something. Okay, so far? All right. So, coming up over here, we're going to end up getting, we've got most of our pieces. Do you see that? So what are we missing? We've got an x squared right here. Do you see this x squared? We have the x squared part for g prime, right? But we have this 3. We need a 3. So how can I get a 3 inside the integral? Well, you're allowed to multiply anything by 1, aren't you? And it won't change the value. So we'll have x squared sine at x cubed, and that's with respect to x. And then we keep one of the 3's out, right? And the other 3 goes in the integral. And so we'll have 3x squared times sine at x cubed dx. Now we have everything we need. Do you see that our g of x is the x cubed? So that's our g of x. And then we have all of our g prime of x, right? All of our g prime. You know what? I was doing that in, I was doing the g prime in green, sorry. G prime of x, we now have that, okay? And our g of x, doing in blue, is the x cubed here. Okay, I just changed up the colors to match with what we did before. Okay? So now what's going to happen is we can complete our integral. So now this is going to be 1/3 times our capital F of x, which is negative cosine at our our g of x, which is x cubed plus c. So at the end of the day, we'll get negative 1/3 cosine at x cubed plus c. And this was all prep work here. Okay, next up, we'll finish that u sub. So this is the prep work for the u sub, right? So this is going to give us, okay, now we've got the integral of x squared and then times sine, so x squared times sine at u, and then n for dx, what do we have? Good, du over 3x squared. So each of these parentheses are factors, okay? So this is what's lining up with these. So this is our dx, right? And then our u was x cubed. And so now we need to see what divides out. So do you see just the x squared part divides out? And since all of these are factors, that 1/3 can be brought outside, all right, because it's a constant. Just because it's a constant, you know, if that still had an x in there, you could not bring it outside, times the integral of sine at u du. And this, of course, will be 1/3 times negative cosine at u plus c, which is negative 1/3 times cosine at x cubed plus c. Alrighty, so with this one we had to back substitute. And again, I don't care which method you use as long as you can evaluate these things. All right? Okay, so next up, okay, so change of variables, guidelines, right? So when you're making a change of variables, right, you end up, you know, d dx of u is going to be some derivative, right, that you found, some derivative. So really what it ends up being is your g prime, right? So here you're going to have d dx of u would be really g prime of x. Do you see that your u and your g of x's were always the same? So you end up getting dx equal to du over g prime at x. Okay, so that's how I differ from the author. Your author says, oh, I'm going to isolate du instead, and you'll end up with g prime of x dx. Okay, that's what is how it's shown in your text. But honestly, if you're going to do it that way, you might as well just use pattern recognition. All right, so here we go. The next step that you need to do is you need to rewrite the integral completely in terms of u, right? So when you do that, what do? Right, so here let's talk about what we did with the I guess we can just sort of make one up, right? So here let's just say we're working with the integral of, I don't know, let's do something fun. Of, make sure it's not something from that I already have. Okay, so x to the 5th plus 2 times 3, let me write it better. So let's say we have 3x to the 4th times x to the 5th plus 2 raised to the 80th power with respect to x. Okay? So here, basically, you got to choose your u substitution. So in this case, what's it going to be? U is equal to, good, x to the 5th plus 2. Right? So that's your u. For this particular problem. Okay, now you come back here, right, and you say, okay, well, d dx of our u, which was x to the 5th plus 2, is equal to what? Perfect, 5x to the 4th. Okay, so far? So, isolating dx, you're going to get du divided by 5x to the 4th. Alrighty, now next up, I'll rewrite that integral. So we had the integral of 3x to the 4th times x to the 5th plus 2 with respect to x. Okay, now rewriting in terms of the variable u, what do you have going on? Well, we have the integral of 3x to the 4th, oh, this was to the 80th power, sorry, times u to the 80th times, you know what was our dx? Good, it was du over 5x to the 4th. So that was our dx. This here was our u. And so now, do you see that you would have the x to the 4ths go away, right? But you still have 3/5 because this is like a whole, you could put this over 1, this over 1, so they're all being multiplied, right? So really, when you rewrite in terms of u alone, you're going to get 3/5 rather. You can bring that outside the integral, times u to the 80th du. And now you've got them in terms of u. So then the next step would be, oh, okay, I'm going to have 3/5 times, good, u to the 81st over 81 plus c, which gives us what? 3 goes into itself once, into 81 27 times, right? So at the end of the day, this, or not end of the day, but we'll have 1 over, let's see, 135 times u to the 81st plus our constant of integration. Then you back substitute. So you get 1 over 135 times our u was what? Kind of go back up here, x to the 5th plus 2 to the 81st power plus c. And so this is back substituting in your u. Cool? Now you can always check your answer by differentiating, right? So if you recall, our original deal was we had the integral of 3x to the 4th times x to the 5th plus 2 raised to the 80th with respect to x, right? What we want to know is this. Does, okay, so we want to check to see if these are equal, right? So what did we get? 1 over 135, right, times x to the 5th plus 2 to the 81st plus our constant of integration. So what we want to know is is what is inside the integral. So the integrand itself, is that equal to the derivative with respect to x of 1 over 135 times x to the 5th plus 2 raised to the 81st power, and then plus our constant of integration. So we get 3x to the 4th times, this was x to the 5th, I'm sorry, x to the 5th plus 2 raised to the 80th, is that equal to? So this derivative, remember, we'll get it 1 over 135, a constant, right, times 81 times our something to the 80. Our something is x to the 5th plus 2, and then times 5x to the 4th. And the plus c zeroes out. Well, 5 goes into 135 27 times, right? 27 and 81, you'll divide out, I think, does 9 go into both? Or 27 goes into both. So this would be a 1 and this would be a 3. So what we got was, we got that 3x to the 4th times x to the 5th plus 2 raised to the 80th power, right, is equal to 3x to the 4th times x to the 5th plus 2 raised to the 80th power. And they're the same. Check. Now, okay, obviously this could get a little messy depending on how involved your integrand is, right? So my advice to you is to just check your answer if you have time, right? But there is that relationship, right, between the integrand should be equal to the derivative with respect to whatever variable you're integrating with respect to of your result. Okay? So don't forget to change this to the proper output, okay? Capital F at g of x plus c. All right, and again, you change your variable. If you have a t, like we have a t here, you're going to have to change your variable. So now, here we go. So this, of course, is equal to the integral of t plus 1 to the 1/2 with respect to t. So I'll write that over here. Good so far? So now, what do you think? So with pattern recognition, g of x would be, my bad, g of t would be, great, t plus 1. Over here, u is t plus 1. Now, g prime at t is just 1. du dt, so the derivative of the u with respect to t is 1. So dt equals du. Over here, our f of something is our something to the 1/2. Our capital F of our something is going to be our something to the 3/2 divided by 3/2, right? So, which is equal to 2/3 times our something to the 3/2. Okay, now we have them both set up, right? Remember, it's just a little different in the setups. So now what will happen is this will end up being, do you see we have our g prime of t is 1, right? So if you want, you could write that as t plus 1 times 1 times dt. right? So when you match it up, you'll have the 1 is our g prime of t. So this is in terms of t now. I'll just say g prime. And our g, you know, in this case is t plus 1. So coming back, we will have the integral of, oh, and this was to the 1/2, my bad. So now we'll have 2/3 times our something to the 3/2. Our something was t plus 1, and then plus our constant of integration. We're all done. Okay. Using u substitution or change of variables, right? We have our setup here. So we would write this guy as the integral of u to the 1/2 du. And so we got our du was dt. Our u is t plus 1. Okay, so this just gives us u to the 3/2 divided by 3/2 plus c, and we'll get 2/3 u to the 3/2 plus c, and back substituting we'll have 2/3 times t plus 1 to the 3/2 plus c. Alrighty. Okay. So now this one's, you know, similar, isn't it? So we can write this guy as the integral of t times t plus 1 to the 1/2 with respect to t. And I'll just write it in terms of t this time. The integral of f at t times g prime, no, f at g of t times g prime at t dt is equal to capital F at g of t plus our constant of integration. And then, of course, the integral of f at u du is equal to capital F at u plus c. So pattern recognition first. And this is u sub, change of variables. So now we've got the integral of t times t plus 1 to the 1/2 dt. Now this is the one, okay, where pattern recognition is not going to work out well. Let's set it up. So do you see that g at t is t plus 1? So that's okay, right? Now, I mean, I guess you could sort of do it this way. G at t is t plus 1. Over here we would say u is t plus 1. So g prime at t, again, will just be 1, right? And du dt is 1. And if you go to set it up, right, so our capital, our f at our something, right, is still going to be our something to the 1/2. So our capital F, no, actually, you know what, we need to work with it more. We need to work with it more. So this is where pattern recognition kind of sucks, okay? because it would end up being more complicated to show you. It sucks because we need to rewrite t in terms of our g at t or u. So this method, I'm not even going to go on because it's not the best way. Okay? Now, coming over here, this is what you're going to see. This is going to give us the integral of t times u to the 1/2, which is all good. And then over here, if I isolate dt, I get du, right? So I'll get my du over here. And I match them up, right? And do you see there's a problem? What's the problem? The problem is this t business, right, that's still here. I do not have this integral in terms of u. So how could I fix this? If u is t plus 1, right? So t would be what? Good, u minus 1 with a little algebra. So here, I'm going to write this as u minus 1, the integral of u minus 1 times u to the 1/2 du. So I've basically changed t and written it in terms of u. Now, what do we do? Good. If you get this far, don't screw it up there, right? You've got a binomial times a monomial now. So what we've done is we've basically taken the binomial expression that's to the 1/2 power, which we can do not much with, and changed the 1/2 power to something that's a monomial. And the binomial now is raised to the 1 power. It's u minus 1 to the 1 power. So what that enables us to do is use algebra to write it like this. So you multiply and you get u to the 1, u to the 3/2 minus u to the 1/2 du. Good so far? Okay. And now this is something that just follows the basic rule, right? It's you know, that power rule, and you've got a difference, right, of two monomials that are raised to the power rule, and they're not composites anymore. So when we go to integrate, do you see you'll get u to the 5/2 over 5/2 minus u to the 3/2 over 3/2 plus c, which gives us 2/5 u to the 5/2 minus 2/3 u to the 3/2 plus c. Whoops. And then back substituting, what will we get? We'll get 2/5 times t plus 1 to the 5/2 minus 2/3 times t plus 1 to the 3/2 plus our constant of integration. All right, so that's one of the tricky ones. All right, you're going to run into tricky stuff. This is one of the tricks, and yes, you do need to know this for the exam, right? So this type of problem, okay, and you'll have to recognize the format of it, right, is where this type of thing is you want to use substitution, and you end up doing that trick where you rewrite this one in terms of u. Okay? All right, so next up, again, we got to fix this one. This is capital F at g at x plus c. So here we go. My advice is, for C and for D, I'll fix this guy here. My advice is that you go and you try these on your own, as well as, your E. Try them on your own and then play the movie, see how you did. Okay? Okay. Good luck. All right, let's see how you did. So we've got this one here. We've got x to the 4th plus 2 over x to the 5th plus 10x raised to the 5th power with respect to x. So it's often good to rewrite this. If you have a fraction in there, rewrite it as a product, and sometimes it comes more clear what your g of x is or what your u is, right? So here, do you see that this is equivalent to the quantity x to the 4th plus 2 times x to the 5th plus 10 x's raised to the negative 5 with respect to x? So I'll write that over here as well. Okay. So now, let's check it out. So here, what do you think all your stuff should be? I'll leave a space. So we would have, let's do it down here. What's your g of x? Beautiful. Your g of x is x to the 5th plus 10 x's. And so g prime at x will be 5x to the 4th plus 10, right? Now, remember, we want it to be kind of like that x to the 4th plus 2, right, over there. We need to get it in terms of that. So isn't g prime of x, if you factored out a 5, wouldn't it be 5 times quantity x to the 4th plus 2? Okay, so far? So then, our f of something is something to the good, negative 5. Something to the negative 5, right? Which means capital F at our something is going to be our something to the negative 4, because you're increasing by 1, over negative 4. So our capital F at our something is just going to be negative 1 over 4 times our something to the 4th. Okay, so far? So, matching everything up, we'll have our g of x, whoops, sorry, that's for g prime. Actually, we don't have it quite yet. Do you see that we have our g of x here, right? That's our g of x. We almost have our g prime, but what are we missing? Good, we're missing the 5. So we need to rewrite this guy as, remember, you can multiply by 5 over 5, right? Times the integral of x to the 4th plus 2 times x to the 5th plus 10 x's to the negative 5 dx, which is 1/5 times the integral, we needed this 5, times x to the 4th plus 2 times x to the 5th plus 10x's to the negative 5 with respect to x. So now we have everything we need for our formula, right? We have our g prime is this, right? So that's the g prime part. Dx is dx. And then we have, this is our g of x. So now we can go to over here. At the end of the day, well, our next step will be, actually, our next step will be we will get from up there, we'll get 1/5, our capital F at something ended up being -1 over our something to the 4th in that denominator. And what's our something? X to the 5th plus 10 x's, and then plus c. So then rewriting it, we'll have, oh, and we have, I forgot my 4, this 4, and that's a negative. So then we will get -1 over 20 times x to the 5th plus 10 x's to the 4th. You can write these with negative exponents if you prefer. Right? It's fine. And we're all done. Okay? Now let's see what happens with change of variables, or u sub. So over here, u is going to equal to, good, x to the 5th plus 10 x's. So differentiating both sides with respect to x, we will get 5x to the 4th plus 10, right? And here, again, you're going to see you've got that x to the 4th plus 2 part. So you're going to want to kind of recognize that, hey, it might be better if I factor out this 5. And so now, isolating dx, you would get du divided by 5 times x to the 4th plus 2. All right, so next up, whoops, we will have, this will be equal to x to the 4th plus 2 times u to the negative 5, and then in for dx we had du divided by 5 times x to the 4th plus 2. And matching up our stuff, this is our dx, just substituted that bad boy in. Our u was this guy. And now we have to see what can divide out. So do you see x to the 4th plus 2 divides out? And when we rewrite, we have the integral of, actually 1/5, let me write that better, we can pull that 1/5 out, times the integral of u to the negative 5 du. So that gives us 1/5 times u to the negative 4 over negative 4 plus c. So then, whoops, we get -1 over 20 times u to the negative 4 plus c, which is -1/20 times our u, which was x to the 5th plus 10x. That's to the negative 4 plus c. So you can leave it like that, or you can write it like we did below, which would give us -1 over 20 times x to the 5th plus 10 x's, that raised to that positive 4 now that it's in the denominator, plus c. So either one works out. Groovy? Okay. Now, what about this next guy? How'd we do here? Looks a little scary, right? Um, get over it. You're going to need to know these real well. Now, again, with the pattern recognition, I'm just going to show you how fast that would go. All right, with the pattern recognition. So here, you know, when I see that I'm going to end up having, I'm going to write this here a little bit better. So we'll have the integral of sine at 2x, the quantity squared, times cosine at 2x dx, right? So when a person uses pattern recognition, right, I mean, I can tell right away that I'm going to need a 2 here. Do you see that? And to adapt for that, I got to multiply by 1/2. The reason I needed a 2 right there was to get my g prime, right? Because if g is sine at 2x, g prime is going to be 2 times cosine at 2x. So then I could go directly from there and I could say, okay, I'm going to get 1/2 times sine at 2x cubed over 3 plus c, which is 1/6 times sine at 2x cubed. And so I just wanted to show you that because pattern recognition really is a little faster. And if you want to be able to do this, especially when you're in Calc 2 and you're on section like 8.3, I think it is, the more you're good with the pattern recognition, the less scary that section will end up being next semester, right? So here we go. If we use u sub, that's perfectly fine right now. We're working with, you know, sine at 2x, the quantity squared, times cosine at 2x with respect to x, right? So our u is going to be I'm going to do it a little lower. Our u is going to be perfect sine at 2x. du dx is equal to 2 times cosine at 2x using the chain rule. Isolating dx, we're going to have du over cosine at 2x, okay, over 2 times cosine at 2x. All right, so now let's see what we've got. So this is equal to u squared times cosine at 2x times du over 2 times cosine at 2x. So this was our u. Dx was this guy. And look at that. The cosine at 2x's, whoa, the cosine at 2x's divide out. Cosines at 2x divide out. And now we're left with 1/2 times the integral of u squared du, which is 1/2 times u cubed over 3 plus c, which is 1/6, and my u was sine at 2x. Alrighty? How are we doing? Awesome. Okay, so part E. Part E, what do you think? We just did the integral of sine at 2x quantity squared times cosine at 2x, didn't we? So do you understand that if you have sine at 2x be your u sub, it won't work, right? If you say u equals sine at 2x, right? Du dx is going to be 2 times cosine at 2x, which we don't have. In this problem. Okay, sad face, sad face. So, from the double angle formula for the cosine function, all right, I'm going to show you the derivation of it, and then I'm going to highlight what you need to definitely have memorized. So, if you recall, cosine at 2a, it had 3 ways it could be. It could be cosine squared at a minus sine squared at a. It could be two, and this would be substituting in sine squared, 1 minus sine, or this would be substituting in 1 minus cosine squared of a in for sine squared of a. You would get 2 cosine squared at a's, right? And that would be, let's write it out. What the heck? So cosine at 2a would be cosine squared at a minus 1 minus cosine squared at a. And so we're plugging this in for sine squared at a. So what happens is we would end up getting 2 of the cosine squared at a's and then minus 1. Good so far? Now, if you isolate, so if I have 2 cosine squared at a, I'm adding 1, I'm just kind of rewriting it, so then you would have is equal to 1 plus cosine at 2a, and dividing by 2, cosine squared at a would be 1 over that would be 1 plus cosine at 2a all over 2. So this is one thing that you absolutely have to memorize. This guy is super important. Okay, now the next one is going to be something we can use for this problem. So the next one is you're taking your cosine at 2a. I'll just rewrite the beginning stuff, right? So that's one formula that you learned in pre-calc. This was another formula you learned, and it comes from this stuff here, right? The third formula is when you plug in 1 minus sine squared of a into that cosine squared of a. So you would get cosine at 2a is 1 minus sine squared at a minus sine squared at a. So all I did on this one was in for cosine squared at a, I plugged in 1 minus sine squared at a. So then you're going to get cosine at 2a is 1 minus 2 of these sine squareds at a. And that's the third formula you would have learned in trig. Now what we're going to want to do is isolate the sine squared at a. So you'd end up with 2 times sine squared at a is equal to 1 minus cosine at 2a. And then isolating the sine squared at a, you would have 1 minus cosine at 2a divided by 2. This is another super important thing that you need to know. Okay? And you're going to use it all through Calc 3. So just get them in your brain. So these guys, super important to know. And you use it in a case like example E. So here, for example E, we're going to say, hey, this is equal to what? So this guy is going to be equivalent to the integral of 1 minus cosine at 2 times 2x, because my a this time is 2x, all over 2 with respect to x. Good so far? So this is going to end up being the integral of 1 minus cosine at 4x all over 2 with respect to x. Now on something like this, I highly recommend that you split the integral, because many times people make mistakes for this guy. So this is going to be the integral of 1/2 dx, I'm dividing through by 2 and splitting the integral, minus, I'm going to bring the outside, the 1/2 outside on that one, 1/2 times cosine at 4x dx. So now our setup is done. So this one, just be careful, you know, this whole integral is equivalent to all of this. Now, look at the first integral. It's a constant. It's the integral of a constant with respect to x. Do you see? That's a super easy one, right? That you've been doing that one for a while now. But the second one, what do you think? Is that a composite function? Is cosine at 4x a composite function? Yes. And so let's just do it as a u sub, okay? So our u is going to be 4x, and du dx is going to be 4. So isolating dx, we'll get du divided by 4. So now, plugging in what you have. So the first integral, do you see, will be completed at 1/2 x. So this whole thing here, this integral, is done here. We're going to do the plus c at the very end. Okay? Minus 1/2 times the integral of. So cosine at u, and then what do we have? What was dx? It was du divided by 4. So that's going to give us 1/2 x minus, do you see, 1/2 times 1/4 is 1/8 times the integral of cosine at u du. Now I can integrate it, and I'll get 1/2 x from that first result minus 1/8 times sine at u plus c. But what was our u? Good, our u was 4x's. And now you're done. Okay, so here we go. Let's match our stuff up. So we only needed a u sub over here, and the u sub was for 4x's, right? And this is where we back substituted. And then our dx was du over 4, right? And we had gotten that over here. This was over here. And then we finished her off, okay? So, you know, just in case. Okay, so there's some substitutions that are so useful we note them down explicitly. You don't have to memorize them because, you'll get used to it pretty soon and you'll just be able to use pattern recognition. But here, something called the shifting rule for integration basically means that if A is a scalar or a constant, right? Do you see that d dx of x plus a is just going to be 1, right? And so when your dx is the same as your du, right? Or if your g prime of x, if you're using pattern recognition, is equal to 1, then you don't have to worry about this, right? So basically, this situation where you could use something like this would be, let's say we had the integral of let's do the cube root of x, and it can be minus, right? It could be x plus a, it could be x minus a, it doesn't matter. But if the minus was in front of the x, you have to be careful. So let's call it x minus 8 dx. Well, isn't that equivalent to the quantity x minus 8 to the 1/3 power with respect to x? So if you go through and if you do your u subs, you would get, u is x minus 8, du dx is 1, and you could say to yourself, I can just kind of go from there. I can use that shifting rule. And so literally what you'll get here is you'll get your something raised to the 4/3 over 3 plus c, and that something is the x minus 8. And I was able to just go directly to that because the derivative with respect to x of x minus 8 is just 1. Okay? Oh, and I'm sorry, it's not over 3. I'm making shit up. It would be x minus 8, it would be over 4/3, right? Which would give us 3/4 times x minus 8 to the 4/3 plus c. Okay. All right, so now there's also a scaling rule for integration. All right, scaling rule. So if you have f at bx dx, then basically you end up always getting this. And an example of that was that integral. So if you have, I don't know, let's see we had the integral of, the integral of let's do one of the trig ones. So let's say we had the integral of secant squared at 5x with respect to x, right? So here, be careful with these because remember that the derivative of which function has an output of secant squared of something? Good, the tangent function, right? So basically, in this case, your u would have been 5x, right? Du dx is 5. So then when you go over here, dx is going to be du over 5. So it's the b is 5 in this case. So here, if you recognize that, you can go directly and you can say, I know that this is going to be 1/5, right, times tangent at 5x plus c. Right, so in this case, b was 5. In this case that we just did, a was -8, right? Okay, so now we have change of variable for definite integrals. For definite integrals, this is super, super important. If a lot of the professors at Maricosta College require you to change the limits of integration, so to where they're in terms of u. There are two ways a person can do this, though. All right, you could evaluate the indefinite integral, right? Basically, find your capital F at g of x. If you have a composite, you would have a composite. Your capital F at g of x, and then, once you figure that out, go back and finish the problem. All right. The best way, honestly, is just change those limits of integration. So let's see what we have going on here, right? So again, what was a good rule of thumb if we change this to a product? So we'll have 3x times x squared plus 5 to the negative 2 with respect to x. And so now, and I'm just going to use a u substitution. So for your u substitution, what would you do? Good, you would have u is equal to x squared plus 5. And du dx, I'm leaving a space on purpose, is equal to du over 2x. Okay, so far? So now what we do is we can literally equate these things, and we're now going to go from the integral from 6 to 14. That's from over here, right? Are u at 1 and u at 3? And then we're going to have our 3x, and then this is going to be u to the negative 2, and in for dx, we're going to have du over 2x. So this is our dx from over here, and then this is our u, and that was from over here. Okay, so far? Now let's see, make sure this x divides out, and it does. And so now, rewriting it, we are going to have 3 halves times the integral from 6 to 14 of u to the negative 2 du, which is going to give us 3 halves times u to the negative 1 over negative 1, evaluated from u equals 6 to u equals 14. Now, this is equivalent to negative 3 halves. I can factor that out to make it easier to compute. And then u to the minus 1 is 1 over u, and we're going from u is 6 to u is 14. So this will give us negative 3 halves times 1/14 minus 1/6. So then that gives us negative 3 halves times, let's see, this would be 84 if I multiplied them together. So we'd have 6 minus 14. So this would give us negative 3 halves times negative 8 over 84. And 2 divides 8, 4 divides 84, and 3 divides 21. So let's see what, after all the dust clears, it looks to me like we're left with positive 1/7. Good so far? Awesome. All right. So, benefits of this method. You don't incorrectly equate limits, right? If on this step here, if I had wrote this is equivalent to the integral from 1 to 3 of all this, it's incorrect, right? Because these are limits for x, these are limits for u, limits of integration for u. So basically, a lot of times what people do is they're like, I feel weird about changing those limits of integration, right? I'm just going to keep saying from 1 to 3, and then I'll back substitute at the end. But it's not correct to equate them. So, if you're totally freaking out about changing limits of integration, what you could do is find the indefinite integral first, right? So, if you went ahead, so this is the best way for when you're starting, okay? But an alternate way would be find the indefinite integral and then go back to the problem, back to the original, and plug in original limits of integration. Okay. All right, so I'm going to say C above, and we'll do the same problem, okay? So here we go. Oh, what was our problem? 3x over, so we had this integral from 1 to 3 of 3x over, was it x squared plus 5? X squared plus 5, the quantity squared, with respect to x, okay? So, remember that we rewrote that as the integral from 1 to 3 of 3x times x squared plus 5 to the negative 2 with respect to x. And this method is really more for people that like the pattern recognition, okay? If you're doing the U sub, it's way better to do what we did below. But if you're a pattern recognition person, right, what you would see is that what are you going to need, right? You're going to need to have a 2x, aren't you? Because your g of x is x squared plus 5. So here, if I bring out this 3 and I multiply it by the integral from 1 to 3 of x times x squared plus 5 to the negative 2 with respect to x, recognize that you need a 2 right here, don't you? You need a 2 multiplied to the x. So if you divide this one by 2, you'll end up with 3 halves times the integral from 1 to 3 of 2x times x squared plus 5 to the negative 2 with respect to x. So this, by the way, is using pattern recognition. This method, okay? And then, of course, that's going to get us to 3 halves times x squared plus 5 over negative 1, x squared plus 5 to the negative 1 over negative 1, evaluated from, now do you see you're on your x limits are fine, from x is 1 to x is 3. So that's going to give us negative 3 halves times 9 plus 5 over, actually I'm going to say 1 over 9 plus 5 minus 1 over 1 plus 5. Oh, and look what you get. You get negative 3 halves times 1/14 minus 1/6. and we know that that is equal to what we got down there, right? So, which is a seventh. Okay, so far. Now, this alternate way, so that's the pattern recognition way, right? The alternate way would be to say, okay, I'm going to actually insert a page here. I'll just keep it the same. Okay, so you would, again, you'd have this definite integral from 1 to 3 of 3x over x squared plus 2 plus 5 to the negative 2 with respect to x. Well, from the pattern recognition way, with this one, we would say, okay, consider the indefinite integral. The indefinite integral of 3x over x squared plus 5 to the negative 2 with respect to x. And let's say you're a u sub person, and so you know that u, which we said was equal to the integral of 3x times x squared plus 5 to the negative 2 dx. And let's say you're a u sub person, but you don't like changing the limits of integration. So you would go through and you would say u is x squared plus 5, du dx is 2x, so isolating dx, I'm going to get du over 2x's, right? And so then you would say, okay, this is going to be the indefinite integral of 3x times u to the negative 2 times du over 2x. Okay, so far? And then you would say, oh, okay, you know, this is the x's divide out, you know, this was my u was this guy from over here, my dx is this guy from over here, right? And then so you would say what? Oh, this is going to be 3/2 times the indefinite integral of u to the negative 2 du, which gives me 3/2 times u to the negative 1 over negative 1, which plus c, which is negative 3/2 times 1 over u, which gives me at the end of the day negative 3 over 2 times x squared plus 5. And that's just to the 1 plus c. Well, this right here is your capital F at g of x, okay? So what we would do now is we would say, so therefore the integral from 1 to 3 of 3x over x squared plus 5 squared with respect to x is equal to negative 3 over 2 times x squared plus 5 evaluated from x is 1 to x is 3, because you did all that work from over here, right? So, and then you would, so then, because you've back substituted, you would say, okay, that's negative 3/2 times 1 over 9 plus 5 minus 1 over 1 plus 5, which gives us, as I'm sure you're tired of seeing, negative 3/2 times, that's a 14th, so that ended up being 6 minus 14 all over 84, right? Which gave us negative 3/2 times negative 8 over 84, which again, 221, and this is going to be the 2's divide out, 3 goes into 1/7. So we end up at the end of the day with positive 1/7 for the 500th time. But the point being is that we found, so this method, you find capital F at g of x from the indefinite integral and then equate this result to the original definite integral and evaluate the limits of integration at the original limits of integration. Okay? Okay. So, now, after all that, let's go ahead and do some other stuff. Okay? So here we go. We've got this tangent squared at x cubed, right? So one thing you might be thinking is that, okay, it might be good to rewrite this, the u as x cubed, and that's a great idea, but then we have this tangent squared at x, so let's work on it a little on the side. Tangent squared at x cubed, right, would equal to, we know that 1 plus tangent squared at x cubed is equal to secant squared at x cubed from our Pythagorean identity. And so if I wanted to isolate the tangent squared function, I would end up getting -1 plus secant squared at x cubed. This one's going to work better because I've got an antidifferentiation formula for a result of secant squared of something, right? So we need to first rewrite this in terms of the integral from 0 to pi over 6 of, let's see, x squared, right, times -1 plus secant squared at x cubed dx. Now for this one, let's go ahead and split that integral, because you're going to find that we won't be having a u substitution for the first one, for one of them. So x squared times -1 is -x squared, and then you have, with your dx still going along, and then you've got it going here as well. Okay, so this will be plus the integral from 0 to pi over 6 of x squared times secant squared at x cubed with respect to x. Okay, so far? Now, notice that the first one, you can go ahead and start evaluating it. You're going to get -x cubed over 3. That's going from x is 0 to x is pi over 6, right? So this here this whole thing here is this. Okay? But the other one is going to need a u sub, right? So do you see that our u would be x cubed? So u at 0 is 0 cubed, which is 0. u at pi over 6, GC will be pi cubed over 216. Du dx will give us 3x squared, and isolating dx will have du over 3x squared. Okay? So, rewriting this guy, we will have the integral from 0 to pi cubed over 216 times our x squared times our secant squared at u, and then our dx is du over 3x squared. So here's your dx from here. Our u was our x cubed from here, and we found our limits from here. So now, let's see what we have going on. So continuing to evaluate this guy, do you see I can pull out a negative, whoops, let's do it in blue. I can pull out a negative 1/3, right? And then I'll have pi over 6 cubed minus 0 cubed. And then over here, do you see that the x squareds divide out? And so I can rewrite this integral as the integral from 0 to pi cubed over 216. I have a 1/3 in front of it, and then I just have secant squared at u du. So this is going to give us negative 1/3 times pi cubed over 216. And then over here we'll have plus 1/3 times tangent at u from u equals what to what? Good, 0 to u equals pi cubed over 216. So continuing, we have that first one will end up being negative pi cubed over, what's that going to be? Negative pi cubed over 648. And then we will have plus 1/3 times tangent at pi cubed over 216 minus tangent at 0. So this is negative pi cubed over 648 plus 1/3 times tangent at pi cubed over 216, and that's it. If you need to get a decimal equivalent, you can, because tangent at 0 is 0. All right, so that one was kind of a bear, wasn't it? And just so you can match up, let's see, okay, so this whole integral, right, matched to this whole thing. Cool? Okay, so let's see what we've got next. Integration of even and odd functions. So basically, if f is integrable on the closed interval from a to negative a, if f is an even function, then you can basically double the integral from 0 to a. So let's suppose that you have, we have the integral from negative 2 to 2 of x squared dx, because x squared is an even function, right? And let's take a look at a picture of it. Oops. So basically, this guy, what it's gonna look like, it'll be a little weird how we do this, but our original function here is our x squared. Trying to figure out how I want to do this. Actually, I'll do it without showing the limits. So this will end up being x squared, and then we're going to have a bound of 0, okay? And this guy we don't really need. Oh yeah, we do. We need this guy, and we need that guy to be graphed. And when we graph this one, we want to see what the area under the curve is. So we're going to basically want to go underneath that curve, right? Enter. Enter. And then we want to go above on this one, because you're basically actually we'll just go below. Okay, so below that guy. We may need to change some colors here. So basically, if we were drawing, this integral, this is what it would look like. So let's look at our window. Let's just go from -3 to 3. And -10 to 10, I guess. Actually, that's fine. To 10. And then our scale can be 1 on that. Okay. All right, so let's look at a picture here. So that is basically, okay. So here, don't you just love technology? So if I grab this guy, okay, so here, if you see the region of interest, right, is we're looking at, because this is really, and you'll learn more about this later, but this is really something where you're doing the area between, or it's kind of like the area between curves. So this one, all the y values were positive. So the blue region, the blue region is, okay, so since f is greater than or equal to 0, the integral from the indefinite integral of x squared dx, is the blue region. Good so far? So now, do you see that you've got symmetry going on there? So what they're saying is the integral from -2 to 2 of this x squared dx would be going from here to here with this bound, right? And so since you've got symmetry going on there, right, here you could just double this half, right? And it makes it just easier. You don't have to, but it would be double the integral from 0 to 2 of x squared dx. Okay? Now, with this guy, an odd function, let's check out what happens. All right? So let's go to, do you guys agree that the integral from, we could still do negative 2 to 2 of x cubed dx. Do you remember that that is odd, right? So let's check out what that would look like, how that would change on the graph, right? So if we just go to our y equals, we're going to change this to, whoops, a 3. Okay, and then graph. Look what happens. So now we're going to take out that 0 as a bound, okay? So let's go to the y equals, right? And I'm going to take this guy out. Just going to clear it. Let's look at this graph. Okay? So basically what we have going on here is let's see, I'm trying to figure out the best way to show this to you. Maybe I can do that twice. Okay, so if I do x is 0, right? And over here I do, again, x is 0, but instead it's going to be above. All right, let's see what that looks like. Okay, that'll work. Okay, so now so the what this represents here, okay? If you go here and you go to x is 2, so basically the region you're going to have is like this. Something like that. So your region here is going to be, you've got this here, which is all going to be negative. And you have this symmetry about the origin, right? So this region, this region right here, and this upper region here are going to literally zero each other out, because if you were having to find the area, right, you'd be taking the absolute value of one of these and then adding the results. But this isn't about area. This is about a definite integral, right, which is more general. So here, the blue regions zero each other out. Because here, the integral from -2 to the integral from -2 to 0 of x cubed with respect to x is less than or equal to 0. And from over here, the integral from 0 to 2 of x cubed dx is greater than or equal to 0. Okay? And they've got that symmetry. So if you have this going on and you know you have an odd function, guess what? You just get 0. Okay? So now let's take a look. All right? So for this one here, there's a couple ways to look at it, right? You can, if you think, in an ideal world, if you think that something is going to be even or odd, right, you can test it, right? So here, f at negative x would be sine at negative x times cosine at negative x, which is equal to negative sine at x, because sine at negative x is negative sine at x, and cosine at negative x is the same as cosine at x. Now, do you see that that is equal to negative 1 times your original function, right? So f is odd. So if you knew all that, you could go and you could say, that's 0, I'm done, right? Let's say you didn't know that. How would we do this problem? How would we integrate this? Well, we would want to do some sort of a u substitution, right? So we could say u is equal to either one, really, right? Sine at x, and then u at negative pi over 2 is going to be what? Is going to be sine at negative pi over 2, which is negative 1, right? U at positive pi over 2 is going to be sine at pi over 2, which is 1. And then du dx will be cosine at x, and dx will be du over cosine at x. So we have it all set up now. So this will be equivalent to the integral from negative 1 to 1 u times cosine at x times du over cosine at x. So matching all our stuff up, this is our dx. Our u is sine at x, and that's from here. And then our limits of integration come from over here. Actually, don't need those. Okay, so now what's going to happen is the cosine factors will divide out, and we'll just get the integral from negative 1 to 1 of u du, which is u squared from u equals negative 1 to u equals 1, and it's u squared over 2. So then what do we get? We're going to get 1/2 times 1 minus 1, because negative 1 squared is 1, which gives us 0. So you can come by it either way, right? It just, if you recognize that something is odd, you can go ahead and apply that. Okay, so same deal here. Let's test to see if it's odd or even, right? So f at negative x is equal to negative x to the fourth minus 3 times negative x squared, which is equal to x to the fourth minus 3x squared, which is equal to our f at x. So f is even, right? And since we know f is even, we can say, oh, this is equivalent to, and there should have been, I'm sorry, a parenthesis here. This is equivalent to the integral from 2 times the integral from 0 to 2 of x to the fourth minus 3x squared with respect to x. And now this one's relatively easy, right? We'll get 2 times x to the fifth over 5 minus 3x cubed over 3 from x is 0 to x is 2. So that's going to be 2 times, so this will give us 32 fifths minus 8 for the upper limit, and you see that the lower limit's going to zero out. We'll have 0 minus 0. So then we'll have 2 times 32 minus 40 all over 5, which will be negative 16 fifths. Okay? All right, so have a fabulous day. Bye.